Hello, welcome to a coding challenge. In this coding challenge, I am going to attempt to make a perceptron. This is part of a whole bunch of videos that I'm doing about neural network-based learning. But in this video, I'm not kind of getting into too much about the whole broader landscape of everything history-wise and future-wise about what's happening with neural network-based learning. In this example, I just want to build with code the simplest model of an artificial neural network possible, known as a perceptron. The concept of perceptron was invented by Frank Rosenblatt in 1957 at the Cornell Aeronautical Laboratory. There's a link here to the original paper, which I will include in this video's description if you want to take a look at that. And of course, you can always find more on the Perceptron Wikipedia page. What is a perceptron? Why am I even here talking about this? So ultimately, I want to look at artificial intelligence, neural network-based machine learning systems that are inspired by and modeled loosely off of the idea of the actual brain. The actual brain being this thing with like neurons and axons that connect to other neurons and dendrites that receive inputs. I actually don't know what I'm talking about. I'm just reading what's ever on this diagram. But a perceptron, and ultimately, I'm going to start building examples and show you examples of lots of these components that are all interconnected, and inputs are coming in and outputs are flowing out. But I want to start with this idea of the perceptron being a model of a single neuron, the simplest possible artificial neural network that we could build. And this will serve as the building block for future examples that I will make in future videos. Okay, so let's come over to the whiteboard for a second. So if the idea of a perceptron is that there is a single neuron, call this a neuron. That neuron could have inputs. Let's say there are two inputs. I'm going to call them x0, x index 1. So inputs 0 and 1. They come into the neuron. Some type of mathematical process happens in the neuron. And then there is an output, which I'll call y, or output. So these are inputs. And again, this diagram, it might look familiar to you if you've watched some of my other videos, because I often talk about this idea of there is some amount of inputs, a long list of inputs that go into some machine learning recipe that processes all those inputs and performs a task. Maybe it tries to classify or perform a regression, but make some sort of output, some sort of prediction. So this is exactly what this perceptron is designed to do. Okay, here's the thing. In order for us to understand and look at all of the pieces of what's happening in here, we need some scenario. So let's come up with a scenario that we can use. So let's say I have a two-dimensional space. You can think of this will be my canvas, my window. And what I'm going to do is I'm going to arbitrarily divide the space with some line. Some points will be on one side of the line, and other points will be on another side of the line. So essentially, what I want to do is use this perceptron for a classification problem. I want to say that these belong to, class A, and these belong to class B. And I'm going to use a supervised learning strategy. So for background on some of this, you could go and watch session 3 of my Intelligence and Learning series, where I do some other videos about classification and regression and using a linear regression model. There's a lot of crossover here. But anyway, you can stay here if you want. I'm going to kind of talk through everything. But the idea is I want to classify these. So I want these inputs to be, so x0, for any point right here like this, x comma y. It's a little bit confusing the way I'm using. I don't love this, because I should really think of the x is input 0, the y is input 1, right? The x is input 0, the y is input 1. The output is class A or class B, the y. So I'm using x and y in two different places in slightly different ways, which is a bit confusing, but hopefully will make sense as we continue to go along here. Okay, but I actually want to say, instead of instead of A and B, what I actually want to say is +1 and -1. So the idea is that my perceptron is going to output a +1 if the point belongs to group A, and it's going to output a -1 if the point belongs to group B. So and we're going to use the technique known as supervised learning. And what supervised learning involves is I am going to ask the perceptron, I'm going to say, here is some input, give me a guess, but I know the correct answer. I'm going to give the perceptron a point that I know should be in A. And it's going to guess either A and B. If it guesses A, I'm going to say, great job, perceptron, you keep on going. If it guesses B, I'm going to say, perceptron, you made a mistake. Let's tweak something about your algorithm to try to get you to the correct answer. And this tweaking is a process known as gradient descent, and it's something that I've also covered in a couple different videos that I will also link to down here. And we're going to go through it as I get through here. Okay? So that's the supervised learning process. Okay, so what is the actual algorithm? What happens here inside the neuron? So here's the missing piece. And there's a few different missing pieces that I'm get to over time. I was stepping on something, I don't know what it was. These you can think of as connections. The inputs flow into this neuron, but are weighted as they flow in. So each one of these connections has a weight. I'm going to say W0, W1. So these inputs are weighted. And what the perceptron does, its algorithm, is to create a sum of all of the inputs multiplied by the weights. That sum is X input times, input 0 times weight 0 plus input 1 times weight 1. Now in this case, the perceptron only has 2 inputs. So this is a very easy formula to write. As you're going to see as I get into future videos, you might realize like, oh, there's 100 inputs or 1,000 inputs or 100,000 inputs. But this same formula is always going to apply. A weighted sum of all the inputs. Input 0 times weight 0, input 1 times weight 1, add them all up together. So that's step 1 is the sum. Step 2, so you could say like, okay, well, you take that and that's the output. But this isn't the output. Step 2 is something called an activation function. Activation function. And this is a key concept in neural network-based machine learning. As I get into future videos, we're going to see there's a variety of different kinds of activation functions. And why might you use this one or this one? And what do they do? And why? But typically what an activation function does is it allows you to conform the output to some desired range, and do things, and in another way, actually, another way to think about it is if you think about that idea of the brain, like you can think of does the neuron fire and continue to send its data along or does it not? So what happens as the data comes out of that neuron? We're going to use, in this particular example, we're going to use a very, very simple activation function. You can think, okay, well, I only want 2 outputs. I want a +1 or a -1. How could I take any number? I can take any number and convert that number into +1 or -1. How would I do that? How about a function called sign? Take the sign of any number n. If that number n is positive, then I get a +1. If that number n is negative, then I get a -1. Okay? So that's the activation function. This is the whole process. It's often referred to as feed forward. The inputs come in. They get multiplied by the weights. They get added together, and then that weighted sum gets passed through an activation function. And then that activation function gives us a +1 or a -1, should the neuron fire or not fire, and that gets sent out, and that's the output. Okay, I'm back from I was just checking a live chat that's going on. If you're watching this as an archive, that live chat doesn't exist, but there are 2 important questions before I move on. Number 1 is, what do you do with 0? I don't know, we could just pick, we could just arbitrarily right now, let's just say this is greater than or equal. So 0 we'll consider plus 1. I mean, in the case, this is just like a toy example just to demonstrate the idea. It's a building block. You know, I don't know how meaningful it is to be able to like classify points in 2D space based on a line in your, but so at this point I'm going to make an arbitrary determination for that. Well, if it's on the line, you know, is it above or below? I'll pick one. The other question that was asked is, well, how do you pick these weights? So this is the essential question, and this is where I have to get to. So the idea is that through the supervised learning process, we want to search for, we're basically doing a search to find the optimal weights, the optimal weight values that will get the best results, those results with the least amount of errors. And so to start, we have to pick something to start. And in this case, we could pick random values. We could just start with the weights at 0. Well, that could be problematic. So there's different ways. This is a big topic in the field of machine learning. When you start a neural network-based system, how do you initialize the weights? Randomly? What kind of distribution of random numbers? Do you do some other kind of like learning process that gets to like a good starting point for the weights? That's a big topic of discussion and research. But for us, I'm going to pick random weights and start to tweak them. Okay, so there's a lot more pieces of this still, but I think I'm going to go and start writing some code, and then we'll come back to pieces that we're missing. I'm going to do this in processing, which is a Java-based programming language and environment. You can find out more about it at processing.org. I will also release a JavaScript version of this that you can run in the browser, so check this video's description for links to both source codes after it's over. Okay, so what I want to do, I want to create a Perceptron class. So we can see here, by the way, I have this slide here. This is the same algorithm I just talked through. Let's just make sure we have it right. The algorithm is, for every input, multiply input by the corresponding weight, sum all the weighted inputs, and then compute the output based on that sum, pass through an activation function, the sign of the sum. So we can see, we can think of like, this could be the point at 12, 4, and these could be the weights of the perceptron. So what I'm going to do for this particular perceptron is I am going to create an array to store all of those weights. And I'm going to say it's an array with 2 elements in it. And in the perceptron constructor, I'm going to loop through all of the weights and give them a random value between -1 and 1. So, oh, whoops, you don't say void with the constructor. I don't remember how to program in Java-based languages. Okay, so this is the constructor. And what I want to do in the constructor is initialize the weights randomly. Okay, now, what are some things the perceptron should do? Well, one of the things it should do is it should be able to receive inputs and then compute a guess, an output. We'll call that a guess. Okay? So let's write a function. I'm going to call it guess, and it should return an integer, +1 or -1. And it should receive inputs, which could also be in the form of an array. Now, I could, if I wanted to, because of the simplicity of the example, I could have done something like float w0 and float w1. I could just sort of have individual variables for the weights instead of an array. But the nice thing about doing this way is this is more flexible, that this we could have, if we reuse this code later, we could adjust the number of inputs and that sort of things with an array. Okay, so first what I need to do is compute that weighted sum. So I'm going to create a variable called sum and initialize it at 0. Then I'm going to loop through all of the weights. And I'm going to say sum plus equal, what do I want to do? The sum of all the inputs multiplied by their corresponding weights. So inputs index I times weights index I. So this is now that weighted sum. I say that second step. Start with a sum at 0, loop through, and multiply all the inputs by the weights. Then what I'm going to do is I am going to return, I need to get the, so then I'm going to say the output is sign of the sum. So it doesn't know what sign is. There probably is a like Java-based function I could call automatically, but let's just write our own. I'm at the top of this code here. I'm going to write a function. I'm going to say int sign, and it gets, I guess I could say it gets any float. And I'm going to say if n is greater than or equal to 0, return a positive 1, otherwise return a negative 1. So this is just that. This is the, so I could write here as a comment, this is the activation function. I could call it activate or something instead. The activation function is a function that receives some value. If it's greater than 0, positive 1. If it's less than 0, negative 1. So no matter what number goes in to the, whatever inputs come in, whatever that weighted sum is, no matter what, the only thing this perceptron can ever output is a 1 or a negative 1. So, and then I can say return output. So now I have basically, if I kind of give myself help, I really want, I guess this is, I want to see the whole thing. This is, if I have all the code for the, almost all the code for the perceptron. A perceptron has a bunch of weights. It initializes the weights randomly, and it can perform a guess by receiving all the inputs, doing a weighted sum, passing it through the activation function. Okay, so now if I were to just create something arbitrary just to sort of test if this is working, I'm going to say float inputs equals, I'm going to just create some random values like -1, 0.5, and I'm going to say print line, oh, first I'm going to say, I'm going to have a perceptron. I'll just call it P for perceptron. P equals a new perceptron. And then I can say P guess inputs. And I can say output, I can say guess, and I can say, what's wrong here? What doesn't it not like? Oh, this should be, sorry, that should, syntax-wise, that should, these are the inputs, that's an array. And I should say, print line guess. So if I run this, how come I can't? There we go. If I run this, we should see, it outputted a 1. Let's run it again. I got a 1. Run it again. Eventually, I should be able to run it a bunch of times. And I got a -1. -1. Okay, so this, I believe, is working. The system works. I have a perceptron object. I can feed in inputs, and I can make a guess. Okay, so we have the overall structure now for the perceptron, and it works. But we need to do more. So here's the thing. We need to create, now if I had an actual data set, if I were to try and classify flowers, and these were sunflowers, and these were daisies, and the x-axis was like petal length, and this was sepal length or something, I could use a real data set here. I'm going to do something really phony baloney. And I think I'm going to like kind of almost be really ridiculous about it, which is that I'm going to say, I'm going to actually just say that anything, do I really want to do this? I'm going to do it this way. Let's do anything that is, let's just consider the line y equals x. Anything that's above y equals x is a +1. Anything that's below y equals x should be a -1. So I want to create a known data set that I can use to train the perceptron. So let's do that really quickly. What I'm going to do is, let me think about this. I'm going to, there's so many different ways I could do this. Whoops, sorry, I got something in my eye. I can edit that out. So many different ways I could do this. I'm going to make a tab called training. And I'm going to make a class called point. And the point is actually just an input array that has 3 values in it. No. Let me think about this. Let me actually have the point have an x and a y. And also a, I don't want to call it class, a label. I'll just call it a label. Okay, so if I make a new point, when I make a new point, I'm going to say x equals a random width, y equals random height. Am I going to run into trouble without just using the pixel coordinates? Let's try just using the pixel coordinates. I don't know if that's going to be a problem. And then the label, I could say if x is greater than y, the label is 1, else the label is -1, right? That should give me everything above. I don't know what's above, what's below. So let's do that. And then let's write a little function called like show, where I'm going to say stroke 0, and I'm going to say if label equals 1, fill 255, else fill 0, and then I'm going to draw a little ellipse at x comma y, a small ellipse, okay? So what I'm going to do is I'm going to make an array of points. I'm going to make 100 of them. And I'm going to initialize them. And I'm going to say points, index I is a new point. And then let's make the size a little bit bigger, 500 comma 300. Then I'm going to do background 255, and for every point in points. This is an enhanced loop in Java for every point in points. I'm going to say p.show. So if I run this, we can see, yeah, I mean, let's make this a square so it looks a little less weird. And I can also draw, just to sort of like see correctly, I'll draw a line from 0, 0 to width, comma height. So you can see I picked all these points. Half of them are on this side and half of them are on this side. All right, so now that I have all these points and I can see them correctly categorized, this is my known training data. So what I need to do process-wise is I need to take all of my known training data one at a time. I need to pass it in, ask the Perceptron to give me a guess. Is it in 1? Is it in 1 or is it in -1? And then I need to do something based on whether it's correct or incorrect. What is it that I need to do? Okay, let's establish something. There are still some missing pieces here that I need to add, but I'm going to keep going. Let's talk about training. Let's talk about supervised learning. Here's what I need to do. I need to take all of that known data. I'm going to take each and every piece of known data. I'm going to take the x and y point and pass it in. It's going to do the weighted sum. It's going to pass through the activation function, and it's going to guess +1 or -1. Plus fun or negative fun? We're having some negative fun right now, I'm pretty sure. So this is going to give me a guess. But I also have the answer, right? So I have both the Perceptron's guess and I have the answer. If I have both of those things, I can compute something known as the error. The error I can think of as, let's say the answer. I always get this wrong backwards, one way or the other, but it's the difference between the correct value and the incorrect, between the correct value and the guess, right? Because if the guess is a +1 and the answer is a +1, what's that error? 1 minus 1, that error is 0. And I actually have a little bit of a diagram here, over here, where you can sort of see these are the only possible correct answers, -1 or +1. So there's only 4 possibilities. If it's supposed to be a -1, I could guess a -1 or a +1. If it's supposed to be a +1, I could guess a -1 or a +1. So these are all the possible errors. The error is either 0, or the error is -2, or +2, or 0. So this is a good starting point. I need to have this error. The idea here, let me come back to the whiteboard. Okay. So remember, what I'm trying to do is find the optimal weights. So ultimately what I want to do is I want to figure out if I want to say, well, the weight should equal itself plus some change in weight. I want to adjust the weight. If there's a mistake, I want to make a tweak. I want to make the weight a little bit higher or a little bit lower, right? Because maybe my weighted sum got me below -1, but it should be a +1. If I make that weight higher, maybe that'll push the output up to positive. So the issue becomes, how do I calculate that delta weight? How should this weight change based on how should the weight change for weight 0, for weight 1, and if there were many, many, many more weights? So the way that this is calculated is with a process called gradient descent. And I have a couple videos where I go through this in pretty large detail. One way of thinking about this, which I'll kind of duplicate here in this video, is this really relates back to a lot of my steering examples. So I have all these steering examples where I have a vehicle that has a given velocity, and it's seeking a given target. So this vehicle has a velocity, and it also has a desired velocity, right? Because if it should be going towards that target, its desired velocity is to go towards that target. So you can think of this steering formula. If you go back to that Craig Reynolds steering formula, the steering formula equals the difference between the desired velocity, the way that I want to go, and the current velocity, which is kind of like my guess. And if I get this steering formula, if I get this steering function, if I get this steering vector and I add it to the velocity, it's going to cause me to turn and go towards that target. So essentially, that's what I want to do here. This steering vector is the error. The desired velocity is the answer. That's where I want to go. The velocity is my guess. That's where I'm going right now. I want to steer in the direction of the error. So delta weight, the delta weight is actually equal to the error multiplied by the input. So it's filtered through the input. What's that error filtered through the input? That's how I change the weight itself. So that's the process that I'm going to do over and over again. And I have a slide here that I think will walk through that in, oops, I'm in the wrong keyboard, here. So this is the process. This is the supervised learning algorithm. Provide the perceptron with inputs for which there is a known answer, and ask the perceptron to guess. Okay, the perceptron guessed. What's the error? Is it right or wrong? Is the error 0? Is it 2? Is it -2? Adjust the weights according to the error, and go back and do it again and again and again. And this is the formula. The weight is changed according to the error multiplied by the input. And there's something called learning rate, which I'll get to in a second. So let's see now. I've kind of explained that in pieces. Let me see if I can now add that to the code. So I'm going to here, whoops. I'm going to now create a function in the perceptron. And I'm not going to call it guess. I'm going to call it train. So this is going to receive some inputs and a target. Right? The difference between a guess is something like, oh, I just want to receive these inputs and provide a guess. With training, I want to receive the inputs and the known answer so I can adjust the weights accordingly. Okay, so the first thing actually that I should do is just get the guess, which is actually guess with those inputs. So since I already have a function that does the guess, I can ask for the guess from that guess. Then what I want to do is get the error. The error equals the target minus the guess. That's the error. So now that I've done that, what I can do is I can go through all of the weights and say each weight should change according to that error multiplied by its corresponding input. So this is that particular algorithm. This is tune all the weights. Okay? So this is like basically supervised learning says, put the data in, get the result. If the result is right, just move along, nothing to see here. If the result is wrong, twist some dials in here to try to get it closer to the correct answer and do it again and again and over again. You keep twisting dials eventually to find that optimal result. Now, there's something important here though. If I go back to this steering example, you could think about, okay, so this is the vehicle, it's going in this direction, it should seek the target. It knows what the error is. The error is the difference between the way it should go and its current velocity. How much should it steer? If I steer a lot, I could actually like overshoot and start going the wrong way in the other direction. But if I steer just a little bit, maybe I'm going closer, but and you realize that we're going to be doing this with lots and lots of data. So one thing that's actually optimal here is not to steer the full amount all the way according to the error, but just some percentage of the way. And that percentage is referred to, it's a key concept here, and it's called, where's learning rate? So what I would actually do here is say that delta weight, what's this +1 here, is the error times the input, or multiplied also by a learning rate. So that's a key concept here. So let's add that into our code. If I come back over here, the Perceptron is going to have a variable, call it LR for learning rate. I'm just going to say 0.1. So now I'm going to say also multiplied by learning rate. So there we go. Now this is going to adjust all of the weights. So we should be able to, if I go back to here, I should be able to now train the Perceptron. So let's go here and say for all of the points. Oh, I did something terrible. Oh, I'm doing some awful stuff here, which is that I used P for Perceptron, and then I'm using a local variable P for points. So let's call this PT for point. Let's actually just call this, I'm going to call Perceptron, I'm going to call this like the brain. Probably like a bad variable name, but at least it says something more than P. So for every point, what I want to do is I want to say brain.train the point, the inputs associated with that point, and the target, pass in the target associated with that point, right? The point, oh, it has an X and a Y and a label. So the target is actually the label. And can I do this? I want to make something called inputs, which is an array, which just has point.x and point.y in it. Is Java going to let me write that? I think so. So this is what I want to do. I want to train the Perceptron. I want to send in every point as inputs. So the x and the y make the 0 and the 1 input. And then I want to send it into the train function with the label, which is the known answer. So if I do that, okay, so in theory it's training and it's doing this. I can't see anything. So now I need some sort of way of tracking how well it's doing. This is going to be tricky, but I have an idea for how to do this. Somebody in the chat just pointed out that, why am I doing the same loop twice? Yeah, that's kind of unnecessary here, but I'm really just trying to separate out different parts of the code. Ultimately, I probably don't need this original loop. But so there's a couple things I do. One is I could actually calculate the overall error. Like I could actually look, and this wouldn't be such a bad idea, and just sort of print that out. I could calculate the total squared error and kind of evaluate how well it's doing. But I want to just actually look at it visually for a second. So I think what I want to do is, let me see here. What's a good way? So I'm going to just actually say guess equals inputs, brain.guess inputs. And then I'm going to say if guess equals point.label. Let's just call this, let's say target equals points label, just to have these in separate variables. If guess equals target, what I'm going to do is I'm going to draw a, I'm going to draw something that's green. I'm going to say no stroke. I'm going to draw an ellipse at x. I just keep typing P5. Y, that's like a smaller size. Else fill red. Well, everything became green instantly. That can't be right. All right, let's not train it. Okay. So we can see, I guess it's just working better than I had imagined. I'm trying to think visually if there's a better, this is like, okay. So let me make the window bigger, and let me make all of the points, much bigger so it's a little easier to see. And let's run this again. Okay, so you can see without any training, everything is wrong. So I'm not, if I add the train function back in, everything is correct. Now, I guess it just like, this is such a simple scenario that it like trained and worked so quickly in like a matter of like 1 or 2 iterations. Me in the chat had an excellent suggestion which I could demonstrate the training process with a mouse click. So I'm going to quickly do that. So what I'm actually going to do is I'm going to take this training out here. I'm going to take this whole loop and just delete this line of code that actually does the training. And I'm going to run it. So now it's not training, and you can see it's got, every time, when I run this, it's all wrong, right? But what I can do now is I can say void mouse pressed, and I can just run the training algorithm. So now what I did is, only when I click the mouse is it going to run through all the data and actually adjust the weights. So now if I run this, you can see, look at this. It's got most wrong, but it's got some right. It's got most right, but some wrong. And now if I click the mouse, a few more are correct, but some more are wrong. Click the mouse again. Click the mouse again. Click the mouse again. Click the mouse again. So you can see it's like changing, and eventually now it's got everything right. And so you can see how that learning process happens over time. It only took 5 or 6 cycles. One other thing that I could do is just train one point at a time. So I'm going to draw everything, but I could say int training index equals 0. So what I'm going to do in draw now is I'm going to say point training equals points training index. So I'm just going to take 1 point and train it off that 1 point. Okay, and then what I'm going to do is I'm going to say training index plus plus, and if training index equals points.length, like if I get to the end of the array, I will just reset training index back equal to 0. So this now in the draw loop, what did I get wrong here? I'm just spelling training wrong. Oh, double equals, sorry. So now in the draw loop, it should be training 1 point at a time. And you can see like it's kind of weird, all sorts of weird flashy stuff is happening. But over time, it should eventually settle into getting everything correct. But as it makes these little adjustments, it's going to get some things wrong and some things right. And you can see now. So again, there's so many other ways you could think about visualizing the training. And you could actually visualize, one thing you might try is actually visualize the perceptron itself. Like visualize the weights, visualize the connection, visualize the data flowing through it. So I'll leave that to you creative people watching this video. So I'm coming towards the end of this particular video, and I think I need to do, I'm going to give you some exercises, and I think I'm going to do a follow-up one that kind of adds, I'm going to give you some exercises, and then I'm going to come back and do another video where I add these answers in. But so there's a couple things here. One is I've got a serious problem, a very serious problem with everything that I've done here. Let's just say, I'm going to, let's say that the space that I'm in is actually this. 0, 0, forget about pixel space or anything. There's a coordinate space where 0, 0 is in the middle, right here, and I want to categorize data as above or below this line. Or maybe, I want to use the same system, but I want to categorize data as above or below this other line. So I want to use a perceptron to categorize the same exact code to categorize both of these two scenarios. Well, in one case, in the orange case, 0, 0 should be a +1. In the black case, 0, 0 should be a -1. But notice something here. If I'm actually feeding in 0, 0 into this perceptron system, no matter what the weights are, the only thing I can ever get out of here is a 0. This is a problem. Because sometimes 0, 0 is going to be above or below. Sometimes it's going to be in class A, sometimes it's going to be in class B. That can't possibly be right. And this is where this idea of a third, I'm going to go and get another color here. This perceptron will actually not work or perform correctly with this generic scenario, other than with having something called a bias. So I need another input, a third input into the perceptron that is always going to be a 1. Input 0 is x, input 1 is y, and the bias is 1. And actually, if you think about this, this is really, I'm really working through the same problem that's from my linear regression with gradient descent videos, where what I'm trying to do is solve the formula. I'm trying, neural networks are designed to generalize a function, to solve a function. And in this case, this very simplistic scenario is actually just looking to solve the formula for this line, y equals mx plus b. And m being the slope is kind of like rise over run, and b being the y-intercept. So this weight, the bias weight, is really there to solve that y-intercept. And these weights are really solving the slope, the rise over run. So that's what we're doing. We're essentially doing linear regression with gradient descent again, but just through this perceptron model. So if you didn't watch those other videos, you could go back and watch them to sort of connect all these systems. So what I want you to do is, I have an example here from the Nature of Code book. This is essentially the same code that I've been writing, but it does two different things. One is it visualizes what the brain thinks the current line is, and also it adds that bias. So if you're watching this video, I'm going to release the code for this video. This, I guess, is part 1 of the Perceptron coding challenge. If you're watching this video, you could go right to the next one, and I'm going to add the bias in and maybe do a bit more with sort of visualizing what's going on here and have a generic formula for a line. But what I might suggest you do is see if you can add those things yourself to this particular perceptron. And then when I get to the end of the next video, I'm going to talk about why this is such a limited system that can barely actually do anything meaningful in machine learning. But it can be a building block for a much more complex system that can do a lot more interesting and powerful things. So I hope you got a sense of what a perceptron is, what the algorithm for how a perceptron works is, and how the feed-forward supervised learning training process of a model of a perceptron works. Because this exact building block, this scenario, is what I'm going to use in the future videos where we start to build more complex neural networks. Okay, thanks for watching, and I look forward to your feedback and thoughts in the comments.